Everyone said this motor had hit its ceiling, that no amount of engineering genius could squeeze more performance out of a design that Faraday himself experimented with nearly 200 years ago. The entire Western motor industry agreed, and then, quietly, something started happening in China that almost nobody was watching. Here's the part that should make every engineer uncomfortable. The axial flux motor is not new. It is not a secret. It has been studied, tested, published, reviewed, and debated in academic journals for over a century. Researchers at some of the best universities in the world had mapped its limits in exhaustive detail, and the conclusion, repeated across decades of IEEE papers and industrial white papers, was always roughly the same. Yes, it is powerful. Yes, it is compact, but it cannot be manufactured at scale. It overheats. It costs too much. It breaks in ways that are hard to predict and harder to fix. By the early 2020s, the motor industry had essentially moved on. To understand why that consensus felt so permanent, you need to understand what the axial flux motor actually promises, without getting lost in the physics. A conventional electric motor, the kind in most cars today, generates rotation by pushing magnetic force outward from a central shaft, the way a wheel radiates from its hub. An axial flux motor does something different. It pushes that force along the axis of the shaft, more like a stack of plates than a spinning cylinder. The geometry sounds simple. The result is a machine that, in theory, can deliver dramatically more power and torque for its size and weight than anything the mainstream automotive industry was building, in theory. The problem was always turning that theory into hardware that survives the real world. The magnetic circuits in an axial flux machine are three-dimensional and deeply sensitive to tiny manufacturing errors. The stator, the stationary part of the motor, sits in a disc shape that makes cooling almost impossibly difficult because heat has nowhere obvious to go. Getting the tolerances right, the fractions of a millimeter that determine whether the motor runs or seizes, required manufacturing precision that was economically viable only in small, expensive batches. Companies like Yasa in Britain and Magnax in Belgium had demonstrated extraordinary results in controlled conditions. Yasa reached a peak power density of 59 kilowatts per kilogram in late 2025, an unofficial world record. But those motors were hand-built for hypercars and aerospace prototypes. Nobody had figured out how to make 100,000 of them a year and sell them at a price that belongs in a vehicle that regular people buy. So when Western engineers looked at the axial flux motor in 2023 or 2024, what they saw was a solved problem with a disappointing answer. The physics works, the manufacturing does not. Move on. And this is exactly where the story gets interesting, because while the West was moving on, a research institution in Ningbo, China, part of the Chinese Academy of Sciences, was not moving on at all. The Ningbo Institute of Materials Technology and Engineering, working alongside a motor company called Pangu Power, was approaching the problem from a direction that most Western firms had never seriously tried. They were not starting with the motor and then looking for better materials. They were starting with the application, an electric vehicle driving 300,000 kilometers over its lifetime, and then designing the magnet chemistry backward from that requirement. This distinction matters more than it might sound. Most motor development works by taking the best available permanent magnet material, neodymium iron boron in various grades, and engineering a motor around its properties. What the Ningbo team described, at least according to Chinese media and their own public statements, was the reverse. They identified exactly what thermal stability, mechanical strength, and magnetic energy the axial flux application demanded, and then they built a magnet material, which they called PGH, high performance magnetic steel, to meet those demands precisely. The result, announced on June 5th, 2026, and amplified by Chinese state broadcaster CCTV, was a motor claiming 25.73 kilowatts per kilogram of power density and 293 newton meters per kilogram of torque density. It was said to operate at speeds above 18,000 revolutions per minute, with durability validated to the equivalent of 300,000 kilometers of automotive use. Now, before you close this video thinking China just lapped the entire world, pause for a second, because this is where the story requires honesty and where the numbers need context that most coverage has not provided. 25.73 kilowatts per kilogram is an impressive figure. It is also a company claim, reported through national media, not yet validated in an independent peer-reviewed journal from IEEE or SAE. Compare it to Yasa's 59 kilowatts per kilogram, and China appears to be behind. But Yasa's number is a short-term peak on a prototype built for a laboratory dynamometer. Yasa's own estimated continuous power density, meaning what the motor can sustain over time in the real world, world is closer to 27.6 kilowatts per kilogram, and the Chinese figure of 25.73 is presented as a production-ready automotive-grade continuous capability number, at least according to the institution making the claim. This is the axis of the entire debate: peak power versus continuous power, a sprinter versus a marathon runner. YASA built the fastest thing anyone has ever measured. Ningbo and Pangu claim they built something nearly as fast that can run all day and be manufactured 300,000 times a year. If that second claim holds up under independent scrutiny, it is not a footnote. It is a different kind of revolution entirely. Think about what 25 kilowatts per kilogram of continuous power density actually means in a car. Conventional radial flux motors, including the ones in most Teslas today, deliver somewhere between 3 and 5 kilowatts per kilogram. That is not a failure of engineering. It is the result of decades of optimization inside a topology that works extremely well at scale. But it means that a motor producing 200 kilowatts in a performance electric vehicle might weigh 40 or 50 kilograms. A motor with the density the Ningbo team is claiming could deliver that same 200 kilowatts in something closer to 8 kilograms. The rest of that weight does not disappear from the car. It becomes available for a larger battery, for better crash structure, for a smaller, lighter vehicle that uses less energy to move itself. Every kilogram saved in the drivetrain is a kilogram the engineer gets to spend somewhere else. And that is a leverage point that cascades through the entire vehicle architecture. Now extend that logic beyond cars and the picture becomes genuinely disorienting. Electric vertical takeoff and landing aircraft, the eVTOL vehicles that companies from Joby to Archer are trying to certify for urban air travel, are absolutely dependent on power-to-weight ratios that radial flux motors cannot provide. The difference between a motor that weighs 10 kilograms and one that weighs 40 kilograms delivering the same thrust is in some cases the difference between a viable product and a vehicle that cannot carry a paying passenger. Axial flux motors at this density do not just improve eVTOL. They may be the reason some of these aircraft can exist at all. Humanoid robots present a similar equation. A robot that needs powerful joints to lift, carry, and balance is fighting against the weight of its own actuators. A lighter, flatter, denser motor in each joint means a robot that moves more like a human and less like a machine straining under its own skeleton. Chinese media coverage of the Ningbo announcement explicitly targeted humanoid robots as one of the primary applications, which is not accidental. The same company making these motors is operating inside an industrial ecosystem that includes some of the most aggressive humanoid robot development programs on the planet. And then there is the industrial and defense dimension, which nobody in mainstream coverage wants to say plainly. A drive system that is smaller, lighter, and more powerful is not just better for electric cars. It is better for unmanned vehicles, for electric propulsion in smaller naval vessels, for mobile systems that need to move fast and carry payload without the burden of heavy drivetrain hardware. The physics of the motor does not ask what the application is. It delivers power wherever it is pointed. So why is China specifically the one making this move? This is the part of the story that should make Western industrial planners genuinely uncomfortable, because the answer is not that Chinese physicists discovered something nobody else knew. The axial flux topology has been published and available for over a century. YASA demonstrated performance numbers that exceeded the Chinese claim. The research base is global. What China has that nobody else currently does, or at least nobody else has assembled in the same configuration, is a vertically integrated system. China controls a dominant share of global rare earth mining and, more critically, rare earth processing into high-performance permanent magnets. In April of 2026, Zhongke Sanhuan, one of the leading Chinese rare earth magnet producers, signed a strategic cooperation agreement with Pangu Power specifically to co-develop axial flux optimized magnets and lock that supply into a finished motor product. This is not a supply chain relationship, it is a fusion of the raw material advantage with the end product, removing the possibility that the magnet chemistry gets sold to a competitor. Combine that with Pangu's claimed 300,000 unit per year production capacity, the Chinese Ministry of Industry and Information Technology's recognition of axial flux motors as advanced and applicable technology, which signals direct policy support, and the existing electric vehicle manufacturing ecosystem in China that already knows how to build complex drive systems systems at scale, and you get something that YASA, as brilliant as its engineering is, simply cannot match from a startup in Oxford. This is not about who has the best motor in a laboratory. It is about who can make the best motor cheaply enough, reliably enough, and in large enough quantities to define what an electric drivetrain looks like in 10 years. Here's where the documentary has to be honest about what is not yet proven. The 300,000 unit production line is claimed, not independently verified in engineering audits. The 25.73 kilowatts per kilogram figure has not appeared in a peer-reviewed IEEE or SAE paper with full methodology and test conditions. The 300,000 kilometer durability validation is mentioned in Chinese announcements without detailed independent data on thermal cycling, vibration fatigue, or demagnetization behavior at 18,000 revolutions per minute over time. Engineers who have analyzed the YASA announcement, including independent analysts who work in motor design, specifically flag the difference between peak and continuous power as a place where company claims can legally be accurate but practically misleading. The same skepticism applies here. An axial flux motor spinning at 18,000 revolutions per minute in an automotive environment is also fighting physics that do not get easier just because the magnet is better. Heat has to go somewhere. Bearings under that rotational load in a vehicle that hits potholes and temperature swings between -20 and 45 degrees Celsius are stressed in ways that laboratory dynamometers do not fully replicate. The manufacturing tolerances required to keep rotor and stator in precise alignment across temperature changes and mechanical shock are genuinely difficult. Pangu claims to have solved these problems at scale. The engineering community is entitled to ask for the data. What makes this moment different from every previous axial flux announcement is not that the technical claims are more credible than YASA's. It is that the industrial and geopolitical context has shifted in a way that makes the stakes of getting it right or wrong much larger. If these motors work as claimed and reach the cost points that volume production implies, the competitive pressure on every EV manufacturer built around conventional radial flux drivetrains is not theoretical. Analysts covering the Chinese announcement noted plainly that Tesla should be paying attention, not because Tesla cannot build a good motor, but because the company has spent years optimizing a specific topology, and the manufacturing infrastructure, supplier relationships, and engineering culture built around that topology do not pivot overnight. There is a version of the next decade where Chinese axial flux motors become to electric drivetrains what Chinese lithium iron phosphate batteries became to energy storage, a technology that the rest of the world acknowledged in principle but did not industrialize fast enough, and that now has to be sourced from one place under terms set by one country. And there is another version where the durability data never materializes, where the production line has yield problems that make the economics unworkable, where the thermal constraints that every previous axial flux developer ran into turn out to be just as stubborn as they always were. The industry has been here before with axial flux. Remarkable results in controlled conditions that did not survive contact with mass market reality. Here is the question that this technology leaves hanging. If the axial flux motor has been understood for nearly 200 years, if the performance advantages were documented in the academic literature for decades, if companies like YASA were already demonstrating extraordinary results before any of this happened, then why does it feel like the revolution, if it is a revolution, is arriving right now, and arriving from China specifically? The answer is not a single invention. It is a convergence. Material science reached the point where rare earth magnets could be tuned to specific applications rather than just improved generically. Manufacturing automation reached the point where axial flux tolerances became producible at scale. Simulation tools and computational design reached the point where the tight coupling between electromagnetics and thermal behavior in an axial flux machine could be optimized as a system rather than solved piece by piece. And one country happened to control the upstream raw material for all of it, had the policy framework to coordinate the entire chain from mine to motor, and had an electric vehicle boom large enough to justify building a production line of 300,000 units before the product had a single major OEM customer signed. What you are watching is not a single company building a better motor. You are watching a materials monopoly being converted into a hardware monopoly, one axial flux production line at a time. The motor that Faraday was experimenting with in the 1830s is still recognizable in what Pangu unveiled in June of 2026. The electromagnetic principles did not change. What changed is everything that surrounds them: the magnet chemistry, the manufacturing precision, the industrial scale, the supply chain integration, and the geopolitical will to turn a century century-old topology into a strategic asset. Is China's 25 kilowatt per kilogram motor the breakthrough its state media claims it is? Probably not in the absolute performance sense. YASA is still ahead on the numbers that matter for peak performance, but in the sense that matters for who controls the next generation of electric drivetrains, the question may already have a different answer than most people in the West are comfortable with. Where do you think this goes? If China locks axial flux motors into its industrial ecosystem the way it locked battery chemistry, does the West build its own supply chain? Or does it end up depending on Chinese motors the way it currently depends on Chinese batteries? Drop your answer below, because this is one of those moments where the industry conversation is still open and the outcome is genuinely undecided. What is happening with axial flux motors is not really about motors. It is about whether the next decade of electric vehicles, robots, aircraft, and industrial machines gets built on hardware that one country controls from the ground up. For everything else that is quietly shifting in the technology behind the vehicles you drive, the machines reshaping your city, and the supply chains determining who wins the next industrial era, stay with us.